All right, in this video, we're going to go over section 5.2a, and the objective is I can solve systems of equations that include quadratics. So yesterday in 5.1, or in the last video, 5.1, we talked about reviewing how to solve systems either graphically or using substitution and elimination. So we're going to still be looking to use some of these methods, but now we're going to add in quadratics. But before we do that, let's look at our warm-up. It says to solve using any method. So we could use substitution or elimination, whatever one you feel is easiest. I'm looking at this and I'm kind of drawn to elimination because I see that those x's are really close together. And I'm going to think about multiplying that first equation by a -2, and that will eliminate for me those x's. So I'm going to write this right down here below it. So -2 times x, -2 times -2y, and then -2 times +4. And then I can combine these two equations. So my x's have eliminated, and I'm left with, it looks like just 1y, and that's equal to a -7. So again, this is not my final answer, but it is part of my ordered pair. So I just need to substitute this back in. You can substitute it back into either of the original equations. I'm kind of liking the first one to substitute in that y. So again, I'm using parentheses as I substitute in that -7. So we'd end up with x plus 14 as we multiply those together. And when we subtract 14, we end up with a -10. So the solution to a system of linear equations is where those two lines intersect. And these two lines intersect at -10, -7. So let's look down below the warm-up. It says that we're going to use the three methods, substitution, elimination, and graphing, for solving a system of linear equations to solve systems involving quadratics. So there are three possible solutions to a system that's including a linear and a quadratic. So we could have two solutions, we could have one solution, and we can have no solutions. So let's see if we can draw an example. So if you're watching this video for the first time, maybe pause for a minute and see if you can draw an example of a quadratic and a linear equation, how they could intersect twice, once, and not at all. So I'm just going to draw just a generic. I'm not going to put on a graph or anything. I'm just going to think of a quadratic. Maybe it's pointed up like this. And a linear function, if they're going to have two solutions, that means they have to intersect twice. So maybe my line could look like this. And I could find the 2 points where the line and the quadratic intersect. To have one solution, so again, just kind of a generic parabola, I now only want it to intersect once. So I can't have it going in any kind of a diagonal like I did the first one, else it would cross both kind of sides of my parabola. Well, what happens if I took something, say, like at the vertex, and I went vertical? No matter how that parabola opens up, it's never going to intersect that line. No solution. Well, we know no solution means they can't ever intersect. So maybe something like this. This line is never going to intersect that parabola. So when we have linear functions, we also have an idea of being infinitely many solutions. So why is infinitely many solutions not an option with a quadratic and a linear? Remember, to be infinitely many solutions, the lines are exactly the same. So to be infinitely many, is there ever a time that a quadratic and a line could be right on top of each other? Well, that just doesn't even work. You can't have infinitely many solutions because the parabola is curved and a line is straight. So infinitely many solutions is not possible. So I'm just going to say not possible to have infinitely many solutions. So anytime we have a linear and a quadratic, infinitely many solutions is not a possibility. So everything that we're going to be solving today will have two solutions, one solution, or no solutions. So let's go ahead and look at example 1, where it says we're going to solve using substitution. So good thing we reviewed this yesterday. I like problem A because both of these are already solved for y. So I can use either one of those really quick to do some substitution. How about we take this top one and substitute it into that second equation? So I'm going to replace this y with an x squared minus 5, and it's equal to x minus 3. Well, we've got an x squared and an x, which means we probably need to think about factoring or quadratic formula, something like that to help us solve. So I need everything on the same side of my equal sign. So I'm going to go ahead and subtract my x and add my 3. So that's going to give me x squared minus x. And as I add 3, negative 5 and 3 going to give me a negative 2. Well, I would probably try and play my game first. What multiplies to negative 2 but combines to be negative 1? And if this works, then I don't need to use quadratic formula. But if I can't play my game, then I'm going to need to use quadratic formula. Well, negative 2 times a positive 1 works here. That's negative 2 when I multiply and negative 1 when I combine. So because my leading coefficient was a negative 1, this is one of our easy trinomials, and we can factor. So remember, each of these gets set equal to 0, each of these factors, and then we can solve. So we end up with x value of a positive 2 and an x value of a negative 1. Now remember, I'm not shocked that I have two x values because I can have two solutions. So I now need to plug each of these x values back in, and it doesn't matter to what equation. I'm kind of drawn to the second one just because there's no squared involved. So I'm going to start by substituting in 2 for my x. Well, 2 minus 3 is a negative 1. And when I substitute in my negative 1 for my x, negative 1 minus 3 is a negative 4. So remember, we have ordered pairs. When I got a 2 and substituted it in, I got a y value of negative 1. And my x value of negative 1, when I substituted in, I got a y value of negative 4. So this line and this quadratic intersect each other at these 2 points. Let's try it again on B. Now this one's kind of similar, except for we have a y in the first equation, we have a y squared in the second. So I'm going to go ahead and take, just like I did in the last one, I'm going to substitute in to the second equation here, but notice my y is being squared. So as I substitute, my parentheses become super important because I have to square what I've substituted in. So remember, our exponent of squared means that there's 2 of this expression, which means we need to multiply these 2 binomials together. So negative 2x times negative 2x, so 4x squared, negative 2x times 2, 2 times negative 2x, and 2 times 2, still equaling 2x. So I can definitely see this is going to be a quadratic, and I cannot solve a quadratic unless it's equal to 0. So I'm going to think about it as I'm simplifying, bringing this 2x over also. So negative 4x and negative 4x, that gives me a negative 8x, but I'm subtracting over 2x, so that'll give me a negative 10x, and then I have the constant, and now that equals 0 as I've subtracted that 2x over. So we saw in the last video in 5.1, you can choose, if you would like to, if you see a common GCF, make these a little bit smaller. So I see that all 3 of these coefficients or constants are divisible by 2. So maybe I want to divide all of this by 2, just so I have some little bit smaller coefficients and constants to work with. If you choose not to, that's totally fine. But now when I go to think about playing my game, now I have 2 times 2 instead of 4 times 4, so that's kind of nice. So 2 times 2 doesn't multiply to 4, but combine to negative 5. So a negative 4 and a negative 1 multiply to 4 and combine to negative 5. So this one will require some grouping because our leading coefficient is not a 1. So I'll substitute my 5x with my 2 factors, and I'm going to group my first 2 and group my last 2 and take out my GCF. Remember, in that second group, I need to factor out a negative anytime that leading coefficient is negative. And I regroup the GCFs together and that x minus 2 that they had in common. So now these are each of my factors, and they need to be set equal to 0 and solved. So the 2x minus 1 equals 0, and so does the x minus 2. So we add 1 and divide by 2. And in the second one, we just have to add 2. So there's our 2x values. We need to substitute them back in and find our y. I'm going to substitute back into the first one. It was a nice linear equation. I'm going to start by substituting in my x value of 1/2. So I'd have negative 2 times x, which in this case is a 1/2, plus 2. Well, I know negative 2 times 1/2 is just a negative 1. And negative 1 plus 2 is a positive 1. And then when I plug into that, I'm going to do the same equation. Negative 2, my other x, which was a positive 2, lots of 2's there. As I simplify, I'm going to end up with negative 4 plus 2, so that ends up with a negative 2. So written as ordered pairs, I solved my x. I got an x of 1/2, and the y, when I plugged it back in, was a 1. And when I solved for my x value of 2, and I substituted that back in, I got a y value of negative 2. So again, this linear and this quadratic have intersected at 2 points. All right, let's look at example 3, or C, excuse me. Both of these are, again, solved for y, which is super nice. I'm going to take this time, and I'm going to take that x squared and substitute it in to that first equation. X squared is equal to x minus 3. So again, we've got a quadratic. I'm going to think about subtracting my x and adding over my 3. I can't solve a quadratic unless it's equal to 0. I'm going to try playing my game. What multiplies to 3 but combines to negative 1? Well, the only way I get 3 is 1 and 3. And there's no way using positives and negatives to get a negative 1 from those two. So I know playing my game is not going to work, which means I'm going to go to quadratic formula. X equals negative b. Well, my b is already a negative 1. Plus or minus the square root of b squared minus 4 times a times c. Now, it may have been a while, so remember, your a is the coefficient in front of your x squared, your b is the coefficient in front of your x, and your c is your constant. And this is all over 2 times a, so 2 times 1. So when we simplify, this is going to give us our x values. So negative 1, so that's 1, plus or minus the square root of, so let's see here, we'd have negative 1 squared, so that would be 1, minus 4 times 1 times 3 is 12. 1 minus 12 is negative 11. So I'm not shocked that I couldn't factor this playing my game, because in this case, I end up with imaginary numbers, which means there can be no solution. These two are not going to intersect on a normal plane. It would be on an imaginary plane. And we're not graphing with those or solving with those quite yet. So anytime you end up with a negative underneath your square root, we're going to say there's no solution. There's not any solutions unless you're looking at the imaginary axes. Okay, problem D. Again, I need to do some substitution. I'm going to take that 5x and substitute it into that second equation for the y. 11x squared plus, now be careful here because it's 5x that's being squared. We're replacing all of the y. So now as I simplify a little bit, I have to square both the 5 and the x. So 5 squared is 25 and x squared is x squared. Well, these are like terms, so I can combine those. So 11 plus 25, that's 36x squared. So when I divide by 36, I get a nice 1. And we know that to get rid of the square, we take a square root. And the square root is going to produce two numbers, plus or minus, and in this case, the square root of 1 is 1. So I do have two x values. One is a positive one and the other is a negative one. So when I go to plug these back in, I'm going to go to my first equation. Well, 5 times 1, that's just 5. And to plug in my negative 1, 5 times negative 1 is just a negative 5. So this line and this have intersected twice, at 1, 5, and at negative 1, negative 5. Now, if you look closely, in this equation, we had an x squared and a y squared, which we'll get to in a later unit, but this is actually a circle, not a quadratic. So that's kind of interesting. All right, let's look at the back side of your notes. Example 2, now it says to do this doing elimination. So just like we reviewed in the last video, we want to eliminate by adding one of the variables and they eliminate each other. We want to have the same coefficient and the same sign. So as I look at problem A, I'm already seeing that my y's are exactly the same coefficient and we've got an opposite sign. So I'm ready to eliminate those y's. 3x squared plus 1x squared is 4x squared. And 27 plus 9 is 36. And when I divide by 4, I get x squared equals 9, and I'm ready to take a square root. And anytime I take a square root when I'm solving, I get plus or minus. In this case, the square root of 9 is 3. So now I need to substitute this back in. And it doesn't matter which one I substitute it back into. I'm going to do the second one. I'm going to start with my positive 3. Substituting this into my second equation here. Well, 3 squared is 9. So if I subtract 9, I end up with 0. And if I divide by negative 7, 0 divided by negative 7 is still 0. And when I take a square root, the square root is going to be 0, and I don't need to worry about a plus or minus because 0 is not positive or negative. What about when I plug in a negative 3? I'm going to plug it into that same equation. Nothing about this is going to change because now I'm just squaring a negative, and squaring a negative still gives me a positive. So this time I end up with the exact same values, because it didn't matter if it had a positive 3 or a negative 3, and when I squared it, I ended up with a positive 9. So this time, when my x value was 3, my y value was 0. And when my x value was negative 3, my y value was also 0. Okay, let's do one more. So problem B, we want to eliminate. And we do want these to line up, and we have a little bit of an issue we need to take care of on this one. You'll notice the first equation, we've got a y squared and x squared equals a constant. But in our second equation, that's really just slope-intercept form. I have my y's and my x's on separate sides. So I needed to move this. I can't have my variables on different sides of my equation. And I could change the second equation to match more the first layout, or change the first one to match the second. It really wouldn't matter. I'm going to think about changing the top one. I'm going to isolate the y squared. So let's add 3x squared over to the 6. And if I'm going to be eliminating, I need to have the same variables. And right now I've got a y squared and I have a y. I can't eliminate them if they're not the same variable. So I can square a y and get a y squared. But if I square this y, I have to also square the whole rest of the equation, which we can do. Y squared is easy, but we know on this side that 2x minus 1 now needs to be multiplied to another 2x minus 1, because that's what square means. So we end up with, when we multiply, let's see, 4x squared minus 2x minus 2x plus 1. So just to simplify, 4x squared minus 4x plus 1. So now I've got two equations that have a y squared eliminated. So I'm looking at this one and this one. And one thing I'm noticing in my top one, I don't have just an x term like I do in this bottom one where it has a 4x. So as I rewrite these just to kind of line them up, I'm going to put a placeholder. I don't have any x terms, so I'm going to put 0x so that when I write my second equation, it kind of lines up. Because my second equation does have an x term, a negative 4x to be exact. So if you're ever missing a term, you can fill it in with a 0 if needed. So now when I think about eliminating these, they're not quite ready because I need to have one of these y squareds be a negative. So I'm going to think about this second one, multiplying it by a negative 1. So that's going to give me a negative y squared, a negative 4x squared, plus a 4x, and minus a 1. So now when I go to eliminate, there goes my y squareds. So now I just have 0 y's, but I have a 3x squared minus a 4x squared. So negative x squared, a 0x and a 4x. So that's a positive 4x, and 6 plus a negative 1. So we're trying to solve a quadratic, and when we've been solving quadratics, if our leading coefficient is negative, we usually divide it out. So I'm going to think about dividing every term by a negative, and then I'm going to try and play my game. What multiplies to negative 5, but combines to be negative 4? So negative 5 times 1 should work for this. So that means we have two factors. We have x minus 5 and x plus 1. And both of those can be set equal to 0 and solve for the x value. So x value of 5 and an x value of negative 1. So now we just need to plug these back into our equation. It can be plugged into either of the originals, or you could plug it into either of the equations we manipulated. I'd probably try and keep it easy on myself and probably go back to that linear equation, y equals 2x, and substitute in the 2x minus 1. So when I substitute in a 5, I end up with 10 minus 1, which is 9. And when I substitute in a negative 1, I end up with, let's see, negative 2 minus 1, so negative 3. So my x I plugged in and got out a 9. And my other x with negative 1, I plugged that in and I got a negative 3. So today we're just going to focus on substitution and elimination. So go ahead and self-assess. How do you feel about solving these equations involving quadratics? And good luck on your assignment.